In this work, we present event fields, which use event cameras to capture light fields at high speed, resolution, and dynamic range. RGB cameras struggle to capture high-speed, high spatial resolution videos as they require massive bandwidth. Event cameras reduce bandwidth requirements by capturing sparse brightness changes for all pixels asynchronously. Thanks to their high speed and dynamic range, they have recently been widely adapted to solve imaging and vision problems. Light fields are another technology widely used in imaging and vision for advanced scene understanding, enabling features like refocusing and true depth estimation. In this work, we combine the best of both concepts and develop event fields. Using innovative optical designs for event cameras, we can now capture light fields at high speed, spatial angular resolution, and dynamic range. Event cameras only capture spatial and temporal information, while event fields require angular information. Therefore, we multiplex angular information into either the spatial or temporal dimension, with each having their own relative merits. For spatial multiplexing, we use a rectangular kaleidoscope design inspired by Manakov's work, which allows us to capture a 3x3 grid of angular views with each view at 1/3 spatial resolution. For temporal multiplexing, we place a galvanometer in the optical path of the event camera. By moving the mirrors of the galvanometer at high speeds, we capture angular derivatives of the scene at full spatial resolution. To evaluate the relative merits of the two designs, we built a physics-based simulator using Blender. Please refer to the manuscript for more details. We also developed hardware prototypes for both designs to test on real-world scenarios. Thanks to the event field's high dynamic range, we can now capture snapshot HDR light fields. The scene here has both bright lights and a dim texture. An RGB camera can only capture either the details of the lights by using a short exposure or the dim texture by using a long exposure. However, event fields can capture both at the same time. With the galvanometer setup, we capture a full-frame light field at 40 angular views and 250 FPS. This allows us to post-capture refocus a fan rotating at 300 RPM. We combine the event field data with RGB frames to capture a color event field. We then use the TimeLens algorithm for slow-motion refocusing. Here, we show the ability to focus on a fast-moving Nerf dart. Our technique can focus on the fly, pun intended. We also demonstrate true depth estimation, a common light field application now enhanced with slow-mo capabilities. We believe our work on event fields will inspire others to explore new imaging and vision applications with high speed, high resolution, and high dynamic light fields. Thank you for listening.